Hello, hello. How's it going, Brandon?
Hey, pretty good. How about yourself?
Doing pretty well. Excited for this event. We're gonna get started. You have the live stream going, don't you?
Yes, I
All
do. I got to
right.
turn that off.
Yeah.
Uh,
All right. Well, welcome everyone who's joining us live on YouTube and elsewhere. My name is Nick. I'm a senior developer advocate here at Viam. We can kind of get into a bit more, but I've been at Viam for about 3 years, previously working as a full-time software engineer. And now it's my job to get to build robots and teach people how to build robots as well. It's a lot of fun, and I'm excited to share more about what we have today. So Brandon, kick it off to you.
yeah. Hi, everybody. I'm Brandon, Brandon Shrewsbury. I've been part of VM now for a few months. I'm part of the education team. I helped put together the VM 101 platform and the first class everyone got to take. I've been a huge robot nerd for the last decade. Spent a few years working with humanoids like the Boston Dynamics Atlas, the Valkyrie R5. Worked on the DARPA Robotics Challenge. Spent some time at Disney working on Baby Groot, and then got pretty lucky. Did a stint as a DARPA or a defense PI on a few Army and Navy projects. And now I'm very excited to talk to you all about VM 101.
Nice. What's a PI, by the way? It's not private investigator, I imagine.
Yeah, primary investigator.
Got
That's a
it.
great
Okay.
question. Yeah.
Yeah. And so for those of you who don't know and are here for the first time, heard about this 101, heard about Viam and aren't sure what it is, Viam is a platform to help people build, manage, deploy, dream up the robots they want to build. And it is a full stacks platform. So we have our cloud layer, we have everything that lives on the robot. We'll dig into more about what it can do as we dig into our live AMA here today. And if you have any questions while you're here, I know some of you have submitted stuff ahead of time and we'll be getting into those. But if you have any questions that you want to ask right away as we're talking about different topics and you think of something, feel free to add them in the YouTube chat. And then Camilla behind the scenes will prompt them up to us and we'll do our best to answer them as much as we can. So to kick it off, Brandon, why don't you tell us a little bit about VM 101, what it is, why we built it, what's going on with it?
Yeah, so robotics is a pretty difficult thing to jump into if you haven't spent a lot of time in college or in industry. And we wanted to come up with a way to give people an introduction to both the VM platform and a way to solve real problems. So palletizing is one of those applications that almost every industrial site needs to solve. And so VM 101 really focuses on those robotics fundamentals to, set up a palletizer. We cover the motion planning, how to set up the arm and the gripper, kind of understand the different resources that go into that, and introduce how to use this thing called the VM SDK to control those resources. On the frame system and motion planning, this is one of those core concepts that you need in almost any robotics application. You have this robotic end effector that does something. It needs to do some task, but describing how to control it is not always very intuitive. And every robotic system handles that a little differently. So we basically went in and came up with a way to describe this motion and what we think is a pretty easy to use approach.
Nice.
And I know you've been doing a lot with robot arms. Can you talk a little bit about your experience as well?
Sure. So yeah, I had never touched a robotic arm or even some of the sort of like traditional robotics before I joined VM, and I've been basically a 3-year crash course for me to dig into all of this stuff. And up until about a year and a half ago, I had not ever done anything with a robotic arm other than maintain our robotic arm claw game that we had in the office for a while. It's something they built out, which is incredible. And I hope we kind of build it up again and do something else with it, because we had a U Factory X-Arm 6 that we had just in the middle of this enclosure with a bunch of sort of squeeze balls and an actual robotic or a arcade claw on the end of it as our end effector. And a custom web app that was made in order to navigate the arm around, have it drop down and try to pick up the ball. And just like most arcade games, that claw could pick it up or not. It was not necessarily more accurate than your traditional one, except the fact that it didn't swing around as much on like a gantry system. And we can go over the difference between like a gantry and an arm and all those other things as we dig into that. But yeah, I've learned a lot about, kind of like smaller arms and the bigger arms. Now our industrial ones we start to play around with. And so now I have probably around 3 different arms just in my office now at home, not to mention all the ones we have in the lab in New York City. And so like one of those arms right now is one that we're starting to do a lot more with is the SO Arm 101, or we call it the SO 101 for short. And so this is a 3D printable robot arm with these programmable servos for each of the joints. So there's 5 different joints and then one for the gripper itself. And these are pretty neat because I can just plug it into, my laptop or a Raspberry Pi or any other computer and control it over USB. And then you can hook that up to what's known as the leader version of that. One second, I'll grab that. And this is your companion to your follower of that white version I showed. And so this one can be used to move the other arm as you're moving this one so that you could what we call teleoperate it. And teleoperation can be done in many ways. One way is having kind of a clone of that arm in order to move it around. So when the joints move, they reflect back on the movement of the other arm that's falling around. And then that teleoperation can be used for many things. It can be used for, we can dig into kind of like robot training or imitation learning. It can be used just for helping kind of see what it would look like to test out motions or pick places around a workspace to save positions or record those motions. And so very useful. You can do that also just through like something like the Viam control panel to move the arm around. You could use different controllers. We have VR controllers we use to teleoperate robot arms. I've been playing around with another sort of like 3D controller as well that you can use to not only move the position but orient around using something that kind of fits on your desk. So I've been learning a lot about things like motion planning, using cameras in order to figure out where things live in 3D space and figure out ways to grab them. Reading up as much as I can about things like grasp estimation or trajectory planning or generation, all these sort of concepts that you can dig into once you start to get the fundamentals of something like VM 101 to say, okay, I need to go somewhere, perform an action, pick it up, do whatever I need to do with it, and then go another place, and then figure out also how do I avoid stuff on the way there, which is something that you've dug a lot into as well, Brandon, right? So like obstacle avoidance or being able to plan around obstacles, and what kind of goes into that? Can you tell us more?
Yeah, so one of the things that's really fun about VM is encoding the environment that you're in. So for the people that have used URDFs before and kind of have this experience, setting up simulations, that you need to describe everything in the environment so that you can give it to your motion planner or whatever smarts that you're trying to build. If it doesn't know that it doesn't exist, it really can't plan around it. Mm-hmm. So that's why we have this thing that we call collisions and kind of encode, oh, there's a table here, there's a floor here and a wall. And then as you build these obstacles and build the environment, we make the motion planner aware of these things so that it can figure out exactly how to move the arm or how it might need to think about the environment to go, and navigate around. One of the fun things to do here is to, set up like an obstacle course or set up some stuff around your arm and then tell the planner, find me some solution that can pick up this box and carry it through. And that's sort of step one after you figure out, all right, here are my obstacles. Then you need to come up with your objective. So in addition to navigating around everything, you may have constraints like, I want to pick up this glass of water, but I don't want to spill anything. Mm-hmm. So we also have a way to encode constraints in the motion plan so that you don't accidentally tip stuff over. And there's a few different ways to encode that. And it's a lot of fun to play with those as well. And then on the perception side, you were mentioning being able to see blocks and kind of figure out exactly how that gets translated to something the robot understands. It's usually a tiered approach. It's like first thing you need to do is come up with a way to sense the environment through some type of perception. Could be a camera, could be a depth cloud. Kind of depends on whether the thing you're looking at is really shiny,
Mm,
is it well formed. If it's super awkward, a lot of times you have to go policy route. And you have to build
mm,
some special model that can detect it. And then the process from going to camera to, hey, let's segment something in the point cloud to get some depth information, and then kind of reasoning about that. And if I remember correctly, you actually have a tutorial exactly on that, right? Could you walk us through the tutorial you have set up? Because I think it also includes the SO 101.
Yes, the tutorial that I've written up doesn't include SO101 just yet. That's something we're working on, and it's in progress. That's a little hint there for something else we'll talk about in a little bit. The tutorial I written is on the docs, so docs.vm.com. It has our tutorial section, and we're starting to add in much more content going forward, as well as the archive of old tutorials that we have there. And that is pick and place. So much like palletizing, which could be called pick and place in a lot of ways as well, I guess. Just a certain application of pick and place, right? You want to go and pick something up and place it somewhere else, right? Palletizing, depalletizing, all these sort of like robot arm manipulation sort of tasks tend to lean into what we would call a pick and place sort of workflow. In this case, it's using a UFactory XARM6, a RealSense depth camera, and a finger gripper, as we call it. And it's a 2-finger gripper at the end of the arm. That is our end effector. And so that uses first by going through and setting static positions of like where to pick up the block that might be in front of the arm and where to place it, where you have a safe position for a bin, for example, instead of a pallet like we have in the VM 101. And that gets you started on, moving around an arm, finding ways to save those poses or those positions of the arm, and then even starting to walk through like, what does it take to get towards something? Do I go right towards it, or do I go, as we call it, an approach pose, where you go above the block and then go down versus going straight at it? Because that can have different sort of effects around your environment. And even, like you said before, mapping out what's the table at so that the arm knows to avoid the table when going towards it. How do I visualize that as well in the 3D scene that we have built into the VM app, like you can in VM 101? And then even showing from there, once you have a position and using Python to code that up into a program, all right, now how do I use the camera to dynamically observe the environment? And so we could pull in a computer vision model that I created for just find sort of like colored shapes, in this case finding cubes. And so you can use that as your object detector, get a bounding box or just a square set of points around where that exists from the perspective of the camera and the RGB image you get from there. And then also doing what's called projection or deprojection, depending on which way you're going, in order to then look at the point cloud data or that depth data you're getting from the camera, and then find the 3D position of it, not just from what the camera frame is, but where it is in the world to the robot. And so from there, you can go and plan out a path to pick it up and then place it back in that static position you already set before. And so you get to build on those fundamentals, start to add some more dynamic discovery, and then start to even automate it and deploy code over to the robot. And so at first you're building a program on your computer and communicating with the robot over that peer-to-peer connection that VM establishes from its SDKs to your robot. But then from there, if you want to deploy something that lives on the robot and works autonomously and can even work offline, you can go into what we call a module. And we have some upcoming content around modules. I don't know, Brandon, you want to talk a little bit about that?
Yeah, so it looks like we've got a few questions from the audience. We'll hit the modules one first because a perfect lead-in. So we absolutely are working on VM 102, which is to wrap that palletizer into a module. I'm in the middle of creating it, and we want to make sure it's well polished before we release it. And it goes directly into taking exactly what you've written in VM 101 and pulling out the SDK portions and building what's called a VM module that gets managed by VM server. So one of the great things about the SDK approach is that you can very quickly prototype something. You can reach out to resources. You can call methods, interact with things very quickly. But it means that you have to manage it. You are running it from your console or terminal. If your computer goes offline or you have a network blip, it could bring the whole work cell down. So instead, Viam has this thing that you package nicely. You provide it to the server, and then you define it in your machine resource config. And VM server will automatically pull it, and you can do all kinds of wonderful things.
Hmm.
So over-the-air updates. If you work on some changes and then you push it, VM server will know automatically whether or not it should pull it down, or if you
Hmm.
pin it to a specific version, it'll say, "Woo, I'm good. I don't want that yet. I haven't been told I'm allowed to pull it."
Hmm.
The other thing that it does is it pushes your module to the VM registry. And I love the VM registry. This is one of the most powerful things is that as people develop these modules, if they decide they want them to be public for anyone, or if they just want it to be available to their organization, they can set this visibility and then share it with the community. And there's tons of really cool modules already, all kinds of fun things to do. There's a few other really great things that modules do. They handle, hey, am I supposed to be using this? I have this resource as a requirement. And it handles shutting down gracefully. And then if you have thousands of robots out in the world and they all need access to these updates, it'll automatically pull those for you, which is kind of the extension of the OTA, or the OTA stuff actually directly.
Hmm.
So yes, that will be our next module or our next VM class. Very excited for that one. We also had another question here, Nick. I think this one would be great for you. Can you explain the teleoperation a little more? What does that mean and how do you use it?
Yeah, so teleoperation, kind of going back into like, I am not physically operating the robot, but I'm using it over, some sort of communication, whether that is, from a WebRTC connection like we do with our VM SDK. So if I wanted to, again, the VM control panel in the web app, you can use that to technically teleoperate any of your components that you have, including a robot arm, a mobile base, a gantry, actuators in any sort of way. And so you can use that to operate the arm, move it around, or you can use any other sort of controller. We can hook up a gamepad. We could hook up, like I said before, another arm that is similar in the shape and the way that it moves as the existing arm or existing component you have. And teleoperation, again, is used really well for, you can do, recently there's a form of ML model called a VLA. We can dig a little bit into that as well if you'd like, where a vision language action model or some other type of policies like you talked about, Brandon. So there's one called ACT, ACT, that is often used for training robots by giving them demonstrations. So you can demonstrate a task many, 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 many times, as well as not only using and recording those joint positions or even the position of the end of the arm or your end effector, as you called it before, Brandon, or EE often. Could be a hand, could be whatever you have there, a gripper, in some cases, a custom 3D printed tool at the end. And by recording those motions and any sort of visual input sometimes too, or any other sort of sensors you want. So you could have maybe something like a load cell or some sort of thing that measures pressure at the end of the arm, or depth data, or anything else you want to include into training that policy or that model. And then by doing that many, many, many times, could be hundreds, could be thousands, depending on the type of task you're working on, through teleoperation or even in simulation, you can start to help the model or help the robot sort of learn how to complete a task. And not only do it like in a fluid motion, but even correct itself as it's going towards. And so a big part of these VLAs is that correction side of it. So when we're doing motion planning traditionally, we're saying, I want to observe and go to a spot or a set of spots and then execute. And if I can't make that, then it just kind of, you have to figure out what your recovery mechanism is from there. And if you, and if for a VLA, or it's closer to what we call visual servoing. And visual servoing is when you are saying, I want to go towards something, but I'm gonna constantly check if I'm like on goal, or maybe something is in the center of the image of a camera, or you're using some sort of other input to correct that movement on the way. And VLAs allow you to sort of encode that in an ML model and train it by giving a bunch of demonstrations. And through the language part of it, you could theoretically start to pull in something like a natural language program, or take in audio and speech to text to then command a robot or ask it to do something, or even pull in some other sort of maybe AI agent that can request a sort of task that happens based off of other inputs or any sort of prompts that you give it. And so that's a really interesting area of research, and we're working hard to make that easier to set up for any arm that you have versus something just like the SO101. You could do it with the XARM 6, like I'm doing with another project, or any other sort of robot you want to work with. And so that's a really interesting area of discovery. There's also stuff like world action models that I don't even fully understand yet. I'm still learning about. And so people are trying to help robots learn how to operate in the world using all these inputs in the same way that LLMs were taught how to maybe generate text and predict things and reason based off of a lot of the sort of like training data that's out there of text out in the world, and then even corrections based off of feedback from humans in the loop. So that's a really interesting area there. So we have another one as well. So people are trying to work on modules now. And so if they wanted to get started, I guess what's the best way to get started before this course is ready? And are modules only just for this sort of control code, or is it for other things as well?
Great question. So I think the first thing we should do, this is an excellent time to share my screen. Hopefully everyone can see our docs page. Mm-hmm. So we're very proud of our documentation. I think if anyone ever gets stuck, it's an excellent resource. And then it's not our only resource. So we also have a Discord. Hopefully everyone who's in the site on learn.vm.com has seen the link that can take us here. And it doesn't have to be about Viam. If you ever have any questions about robotics, we're huge robot nerds. We love to talk about this. But for the module question specifically, to build a module, you use our command line interface. It's called the Viam CLI. And this will talk a little bit about all of the things that you can do with the CLI, but specifically when it comes to modules, the build and deploy section describes the exact commands that you have to go through. And there are a few. We have a lot of power here, so you can build modules per organization. You can define a lot of APIs. So there's quite a few steps that go through to scaffold a new module. In general, this should cover everything from beginning to end. But if you do get stuck, I very much encourage anyone who's going through this to hop on Discord and reach out. We love to talk to developers. The question you posed earlier was, what can you do with the module? Does it have to be for control code? Should it be for hardware? And it is actually for any type of interface or any type of hardware. The question really is, who should own the control code and what does it do? If it's, hey, I'm very quickly prototyping this, the SDK is a great way to do it. But if it's something that you really want to either have running on the machine where VM server is running, or you want it to survive a machine reset, or you want to share it with people, a module is the way to go. And like I said, they're very powerful. So I believe this would be an excellent time to jump over to the registry.
Yeah.
So let's do SO101 here. If my search will work. So every single one of these is a module. Someone went through the CLI, wrote some control code or some type of code, could just be a visual actually, and then published it to the registry. And then you can see some descriptions, links to GitHub. We encourage people to fill out their GitHub READMEs as thoroughly as possible because we scrape those for any kinds of descriptions. And let's see. Oops, that was. So a module will describe all of the models that are inside of it, all of the different things that it can do. If it has any applications, web apps. So in addition to making these libraries that a machine can pull, you can also build this really powerful web app kind of automatically that talks to everything, sort of like a script does. And then it includes different platforms. So every library or module that you build, it's usually compiled for a very specific architecture. Whether you're using a Mac or Linux or Windows, it kind of changes the way the binary is created. And within Linux, there's also different architecture. Actually, within all of them, there's different architectures. And we have a way to build those either on your machine or in the cloud to support as many as possible. And of course, this is one of your modules, Nick.
Yes. Done a lot of work on that one. We're still constantly improving it, and you've added things like the simulated version of the SL101 arm, and I've been working a lot on making it easier to do calibration and even teleoperation. The module stuff is really interesting, and you can, as you showed there, it's not just one single thing. It can provide multiple sort of resources, as we call them, as you also refer to them as models, and they can do quite a bit in terms of controlling arms, adding in different functionality. There's always the escape hatch of a generic component, generic service that doesn't fit with one of our APIs, right? And you can version them. You can set a minimum VM server version as well that they can operate on. Do these updates this way. And it's really interesting how much you can do once you start to build into that workflow. Like once I have a script working, I create a module and I start just, I can do my CI/CD, my continuous integration, continuous deployment with my robot code now in the same way I would with, I worked on web apps and web services back in the day. Some of the modules, like you said, can be something like a world state store, which is what powers this sort of visualization in our 3D scene, right? And you've done a lot of experimentation with world state stores and what's even possible, right? So I guess, do you have any sort of insight into like the flexibility that this provides?
Yeah, so developing robot applications over the years, there cannot be enough visuals. Mm-hmm. So as you start writing control code, every single thing that you write, there's a chance for a bug. There's a mm-hmm. chance for something to just kind of go awkwardly if you're doing autonomous control. Observability is key. Actually, I think you can break it down to whether or not you can direct the thing, whether or not you can observe the thing, and whether or not it's predictable. Those are the three key points in an autonomous system to making sure that you kind of understand what's going on. And one thing that I love about Viam's visualizer, besides being in the cloud, which means that you can access it at any time, and you don't need a specific hardware to see what the robot's doing, it also pulls out a lot of the physics and stuff and lets you do that somewhere else so that everything is really responsive. In this palletizing example, we see the arm, we see the boxes that are being picked up. We're not oversaturating the environment. We're just trying to give you all of the key things you need to be successful. And in the scene, you can see that there's, all of the different resources that are attached. You can control different aspects pretty easily. It's like, all right, I want to move move what we call J0 or the base joint. And the 3D scene is completely built off of the world state store. And the world state store controls all kinds of interesting things. It really is the world state. It's like this theory of the robot's universe all in this one object. You can pull the world state store for joint angles, for collisions, for visuals. You can make your own visuals. You can control when things show up and when they need to be hidden. It's really powerful. And the resource setup that we have means that you do have to jump in pretty deep to get a real handle on how everything's working. So I would say that it takes some getting used to, but once you start understanding how all the visuals get set up, it's very, very powerful.
So you could use this for, like we are for simulating the robot, but you could have a mix of virtual objects and physical objects within, maybe have a real arm, and then you have some, things in the world state store to prevent the arm from maybe moving around in certain directions. You could constrain it by having maybe virtual obstacles like we do, not just obstacles that exist in real life. So that's kind of a virtual safety cage, or a virtual that motion planner at least will respect, but the joints won't. And so it's not a complete substitute for something like a physical enclosure and any sort of deployment, but it can be really helpful when you're testing stuff out to have certain safety boundaries defined in either as a configuration or even your world state store to visualize that, right?
That is exactly right. And one of the things that's really, really wonderful, I know you probably are in the same setup. I have a robot arm set up right next to my desk, and it's very, very close to me. So setting up those virtual walls is necessary, very necessary. So we're here to talk about VM 101. I want to jump in a little bit into the course. So if anyone is, watching that hasn't been part of the course yet or jumped in, on the left-hand side, we have all of the content, and the class is broken up into 18 different sections. The first few are concepts, getting registered with the VM platform, setting up the machine, and adding resources. It's kind of your first introduction to modules, even though you may not realize it. And then we jump into the code. So at the very beginning, we provide a lot of the Python code, so it's just copy and paste. And we've had a few users that don't necessarily, they're not used to Python. So the formatting will get you, some of the naming and whether or not things need to be lowercase or uppercase will get you. And then the second half goes into starting to use the motion service. And Nick, I know you've used the motion service a lot. Can you maybe describe exactly how it works and what's going on there?
Sure. So the motion service is something that's built into the RDK, a robot development kit, also known as VM server. And that also serves as our Go SDK. So it could be a lot of things at once. The purpose of the motion service is to help with what we call planning or motion planning. And motion planning, besides what you might call forward kinematics or inverse kinematics, which is really just solving for what is the position of the joints of the arm in order to have it in a certain position in space, or at a certain position in space, what should the joint positions of the arm be? This also adds in solving for, are there obstacles around? And so like you talked about for world state or certain constraints, like you mentioned, I want to move from point A to point B, but always have the end effector, end of the arm pointed down. Also helps with things like, I want to not direct the end of the arm to go there, but maybe like the gripper in your case. So we direct in VM 101 the what we call the frame of the vacuum gripper to go somewhere rather than the arm itself, which allows you to give more accuracy in terms of, I want to go to this point without having to manually calculate for the offset between the end of the gripper and the end of the arm and a bunch of the other math that goes into that. This is also helpful for things like the pick and place tutorial that we talked about earlier. I observe, or the robot observes, where the block is from the perspective of the camera. And the camera is also part of the frame system, and we calculate and we configure it to say the camera lives this in a certain position in relation to the end of the arm. And by having that in the system, now I can say, okay, I want to send the gripper to that block position from the perspective of the camera. And then the motion service takes care of solving for that. It walks our little tree of the frame system to say, okay, well, if the block is in this from the relationship of the camera is from, this map relationship to the end of the arm, which is related to the end of the gripper here, which is related to the world in this way. And so with that, I don't have to solve for all of that manually. I don't have to figure out the inverse kinematics, the Jacobians, whatever the sort of maths around that, what quaternions you need. I can rely on the motion service to do that for me, and also tell me either that it's not possible to go there because I might run into something, or that it might be out of reach even for the arm and what you're sending there. Along with that, you can also potentially set speed limits and acceleration limits in order to say, okay, go here at a certain amount of time. And so it's a really, really flexible and powerful service to use. And so it can be a lot to get into. And you start to explore it a little bit here in VM 101 as we add in things like a timeout to say, okay, only spend this much time trying to solve for it, or adding in potential obstacles, or even another way we call transforms, which is something that might ride around with the arm itself as you pick it up. So the box, once you pick it up, becomes a transform. And so now it exists in the frame system attached to the arm. And so now we can say from there, I want the box to move to a certain location rather than the gripper, which allows you to do a lot more complex movements and to allow for the planner to know, oh, I'm carrying something now. I need to account for this when I am moving around the world so I don't run into other boxes or the palette or myself even. And so it's amazing what you can do once you kind of can visualize it, once you can start to test these things out. And something that's coming up, which I'm really looking forward to, is the ability to preview plans within that 3D scene and even replay plans that fail, so you can see why they fail, or even replay successful ones to see why they worked or what they avoided, or even debug maybe why it made a certain movement. And so we've been building up so much more capabilities in that 3D scene. It's been getting better, better, and better. And I'm really looking forward to see what we can do, going forward and see what other people can do. It is an open source project as well. I don't know if we talked about this already, but Viam at its core is open source. So the RDK, our protobuf API, which we'll get into if people have questions about protobufs, we can talk about that, but it's not super important at the moment. Even a bunch of our modules are all open source. So you can view how the motion planner works. You can view how the SO101 ARM works, how the palletizer demos work, because it's open source on GitHub. And so you can go explore, dig into those, tweak them, fork them, do what you want to make them work for yourself. We had someone in our Discord actually fork the SO101 ARM module in order to account for different kinematics they want to do with their SO101, because it's a 3D printed ARM. So they can go and custom design something and then kind of extend that module to make it work for them, which I think is amazing. So people can, it's not all enclosed, even a bunch of stuff in the module. When you saw in the registry, you could see the README for that. And that is an option. So you can show people the code for that and allow people to contribute to it as well. And it's kind of amazing what's available there. Something we heard we're getting questioned about is for future courses like VM 102, 103 that I know are planned, are they all going to be in simulation, or will there be some hardware-based hands-on courses we have planned as well?
Yeah, what a great question. So we definitely want to do hardware. And there's a question of what is the easiest thing for people to get a hold of. So the SO101 is excellent. It's pretty affordable. We also have a few courses coming out. So VM 103, I think we have a few different versions, which is building a module to control perception cameras like the D405, integrating an IMU, so how to pull out the orientation, the linear acceleration, the angular velocity, and then publish those as a sensor. And we're also looking at how to write hardware drivers for ARMs. So it is kind of an interesting problem. We really want to share the struggles that you have getting physical hardware to work in the course. But it's difficult to give people a real feel without the real hardware. So, with most perception cameras and ARMs, it can be very difficult to, show all of the problems you have with the USB, or the difficulties if you have like reflections in CAN, or if you've got an EtherCAT device, but your EtherCAT master is missing its real-time rates. And those are a lot of things that are hard to simulate. So I think the goal is probably going to be have a little of A and a little of B. We'll have as much as we can do in simulation and still get the core concepts across. And then we'll have stuff that you can only do if you get a sensor, or if you get an ARM. And then we'll teach one specific model, but try to do it in a way that's general enough that it will apply to different hardware. Nick, I know you've written drivers for quite a few different things. How often does writing a driver for piece A work for part B?
Yeah, I mean, so far I think I've written 3 or 4 ARM modules alone, or ARM drivers, for the ones that I have at home or for ones that we want to support. Usually a lot of the, what we call like hobbyist ARMs. So those beginner level ones that a lot of people can get their hands on are very much more accessible, usually within the couple $100 range versus thousands of dollars that some of the bigger ARMs cost. And there's a lot of reusability there. So like once I've done 1 or 2, I know how the pattern to go through, whether or not it's written in Go or Python or C++. There is, having a API to fit becomes really useful as like a cookie cutter sort of format. Things like, especially with ARMs, there's quite a few things you need to worry about. But the biggest things is like, all right, how do I control the joints or read their current positions? And also, how do I figure out the kinematics for it? And kinematics really is a description of the relationship between the various joints of the arms and the links that connect those joints. And when you move them in certain ways, how does that affect the position of the arm in total? And so a lot of people will design kinematics or get them out of a program that they're using to model the arm, and they'll create something called a URDF, or Universal Robot Description Format, if I remember correctly. And there are other ways to describe kinematics. We have one called spatial vector algebra, which sounds so scientific, but it's really a JSON file versus XML for URDF. And there's a lot of similarities into how they describe, the kinematics or relationships of joints and links. And even for things like obstacle avoidance or self-collision avoidance, in this case, what the geometries of the arm look like. So it knows when it moves around, it's not going to run into itself. And so you can find those in different ways and then use those in order to then do your inverse and forward kinematics calculations. So when you want to know, I have the current positions, the current joint positions, and now I want to know where the end of the arm is, or I want to put the end of the arm somewhere. Now I want to figure out the joint positions that will get me there, which can be multiple ways to do that depending on how many joints the arm has, or might be impossible to get there because of how many joints the arm has. So some of the arms like the SL101 or some of the wave share arms that I've worked with are what are called 5 degrees of freedom, which means that they can do quite a bit of positions, but the orientation is not necessarily as free as you want to. So you can't always just move the arm and have the orientation stay the same. So that is where a 6 degree of freedom arm, or even greater, sometimes 7 or 8, allow you to have a lot more flexibility into where you position the arm. And so you have to kind of think about these things, but also VM provides a lot of tools inside of the RDK in order to make that easier to get started. The other side of it gets into details around like, all right, how do I show the 3D models of the arm? How do I figure out like the speed of the arm as it's moving around? And those become a bit more per arm setups. Outside of arms, writing stuff for cameras or for various sensors. I've written, ML model services to run inference on different, sort of runtimes. And I've learned quite a bit on each of those subjects to make them work, but I always know I can fit them to a certain API in order to make them work. Let's see. I was trying to think of some other modules that are really interesting to get into, but I also had a question about, so we talk about simulation for courses. We show our 3D scene, which some people can call simulation. It also can be what we call a digital twin environment for something that exists in real life, and viewing what's happening and showing how the robot is operating in that environment, whether you're there in person or remote. Is that the same thing as simulation entirely? Or you mentioned a little bit about physics. Are there other simulation environments that are worth exploring and that we're looking into as well?
So simulation is a very hot topic these days. There was a question, I think, by one of the audience members about ghost objects. And
Sure.
this is essentially can we make a fake object and train a robot around it? And simulation is really designed to do that. It's to try and encode as much about the real world in an accurate way so you can develop your control algorithms quickly. And one of the great things about setting these sims up is if you get to the point where you can do CI in sim, then you can completely change your workflow. So if you're working on something really hard, like a physics problem, defeating physics, which is kind of humanity's goal in life, at least partially, and physics always wins. So you have a sim, you get your robot to do something like walk across rough terrain, drive over a ramp, get a dirt bike to do a backflip or something ridiculous. Then you try it in real life and it fails. And then you go back to the sim and you're like, all right, which part of this sim was wrong, and make it a little better. And sometimes to get this, it's called sim to real transfer. It's something like getting your policy to understand how your actuators work. Sometimes it's like, I need to change my contact model to really understand this point-to-plane or plane-to-plane interaction. It gets really nerdy really quickly. It's a part I really love. There are so many different simulators, and some do really amazing things that no one else does. Majoko is getting really popular. Does a great job at doing RL training. It is well supported. It's kind of getting integrated everywhere. Its cloud support is kind of so if you're trying to do stuff through JavaScript, the Viz is still in development. Something like Isaac, which NVIDIA put together, it does beautiful USDs. Okay, all of the stuff looks amazing, and you can really train your models with almost very lifelike video. It's great for VLAs, great for like trying to create image models. It doesn't work with RTX video cards, which is the latest brand of NVIDIA video cards. There are like ways around it. So then they came out with Newton, and Newton works for pretty much everything. It's pretty new. Also looks pretty, but there's a lot of trade-offs. If you were to go with Gazebo, which was kind of the original ROS integration, they made SDFs, which kind of spawn off from URDFs. So there's too many to choose from. It kind of depends on what you're doing and what's really important to you. There's some very hidden ones that I really love they kind of treat every collision as an optimization problem. A lot of sims explode. You have two things touch each other, and when you try to get the physics right, they vibrate until they just bounce away because the way they model physics, which is very difficult, kind of just can't handle how stuff runs together. I was thinking, so we've got a lot of questions that we got from the audience beforehand. I would love to rapid fire a few of these to you to get quick answers. How do you feel about that?
Before we get into that real quick, I want to get a poll going so we can, while we're chatting through these. So we've described a couple of courses that are coming up, including building a control module, cameras, sensors, even something about VLAs with SO101. So in the audience, if you could type out your 1, 2, 3, or 4, depending on which one you're looking forward to, we can kind of have that going while we're chatting through some of these questions. Cool.
All right. All right. What kind of sensor can be used for obstacle avoidance?
I mean, quite a few. So I've worked with stuff like an ultrasonic sensor is very sort of one of those simpler ones where it's we can model it as a sensor or even a camera. It's a very low resolution camera because it has a single point. You can have multiple points that says, all right, how far away is the distance of something in front of me? And so that can be used to, you've got several of those around. Your cars often use ultrasonic sensors in order to say, are you getting too close to an object in front of you or behind you as you're backing up? And so that's one way to do obstacle avoidance. And then building on that, you could do stuff with, like you said, cameras before. There are things like LiDARs. And so LiDAR being usually either 2D or 3D is like a laser that's running around with a spinning mirror that's kind of firing it off in many places and then receiving them back to see how long they took. And that can be used for building something like a simultaneous location and mapping map, SLAM. And that can allow for mobile-based navigation. You could use it for, humanoids often use it as well for moving around. I know some of the robot dogs, those sort of things. And so often your robot vacuums, of course, will use SLAM or a mix of SLAM and cameras or just cameras. You can even have, like, I guess it's not necessarily obstacle avoidance, but awareness of like bump sensors can tell you like where something is. And so those are, I'm trying to think of some other ones that you could possibly use. Do you have any other come to mind?
No, I think you covered. The answer is there are a lot of options, and it depends on the use case. But you covered the big ones.
Yeah, you can fuse them all together too. It doesn't have to be one, right? You can kind of take it all as input. Yeah.
Sometimes you have to fuse them together to get everything. So if you have an SO, is the next question. If you have an SO101 arm and you're not using the default servos and you want to use a different set, what happens when you try to use a different set? Does the module still work? Does it depend?
Yeah, it depends. So if they can still communicate in the same protocol. So VTech is one of the makers of these servos that the SO101 is usually based on. And there's a certain brand or model of that, the VTech servo 32, STS 3215, I believe is what they're called. And they come in like either plastic geared or metal geared, but they're still the STS 3215. And that's what the module usually uses for that. So if you want to use a different set of servos, either different models from even VTech, we'd have to extend the current implementation. So we could think about that. It becomes more popular, but right now we're really going for that happy path of like, you built it yourself using the SO101 ARM like instructions, or you're buying a kit off the shelf from someone like Seed Studio or High Wonder or some of the other ones you may find on Amazon or elsewhere. But if there's more support that people want, like, you let us know. You follow up in Discord, you reach out to us, we can look into extending that or help you extend it yourself, like I mentioned before.
So if all of the servos are still using like TTL or RS485, whatever the initial actuator is using, it should just work out of the box, right? It's pretty likely.
Mm-hmm.
Excellent. So I had another question here about pick and place. If you were to describe inverse kinematics in like 3 or 4 sentences, what is it?
So right, we touched on this a couple times, but to be clear, like a kinematics again is the description between a joint or some movement of could be an arm, could be a base, could be a gantry. These are things that move essentially, and the parts that move could be called a joint or a wheel. And as they move, how does that move the rest of the robot in space? That is your kinematics, your description. The forward kinematics for something like a robot arm is saying, okay, I have the position of the arm, like this. Where does the end of the arm exist now in 3D space based off of the relationship between the base of the arm itself? And then the inverse of that, or inverse kinematics, IK often called, is I have the position of the arm, or I want to go to somewhere else. Now, what is the joint position, or what is the estimated joint position of the arm in order to get there? And then from once you have those 2 points, you can start to do stuff like motion planning in order to interpolate. All right, I want to get from here to there. What do we need to do that, to move the arms along the way? Do I move all the joints at once? Do I move them individually? Do I move them over time? All the sorts of stuff that comes up with motion planning.
So it looks like the results are not updating in the survey for some reason, but it sounds like most people are interested in real hardware drivers for a camera and training in VLAs. So
very popular these days. Yes.
Yeah, VLAs are super cool.
Mm.
So we had a question, and it was really about should people get into hardware or should people get into software? And it seems like you really can't get away from either if you're going to do robotics. It's hardware, software, electronics, and if you're building your own business, then it's sales and marketing and a lot of interacting with people. Which part is your favorite?
So I'm very biased towards software because it's kind of that slightly more accessible way to get into it. Like you said before, you can get started with simulation. You can do quite a bit on the software side just to learn about robotics, to test stuff out, and eventually to control hardware. You need software to do that. But you will eventually need to learn about the hardware aspects of things like, how do I wire up things? What sort of power requirements are there? What are the failure modes that can happen with something in the field? And how do I observe those aspects of it? How do I, even chain a bunch of stuff together that may have not fit together before? How do I create my own maybe PCBs? This is like a field of like mechatronics, right? And that's something that's always very interesting to me is like you have to know a lot about a lot of things in order to really build a robot, or you can work with a lot of different people who know a lot of things to build a robot together. So I like to work with a lot of our, hardware engineers at Viam to figure out what I don't know. If I need to design a 3D part, or if I need to build something together, what parts do we have? So it's really fascinating to me that it does have this great intersection between like hardware engineering, software engineering, electrical engineering, mechanical engineering. Like all these disciplines come together to build a robot and to build a very good production robot. And one thing I do like about Viam is we try to concentrate on all aspects of that as much as possible, including the sales and business side. Like we don't talk about it very much, but you can, start to do billing through our platform, authentication, all the stuff that people who are building a robot think about last when they need to go and provision a robot out in the field or observe them. Those are built into the cloud platform, make it really easy to do those things when you have a working robot. Now you're building a robot business on top of that. Some other people have asked now in terms of AI models best suited for autonomous robots or hardware GPU platforms to recommend. I mean, I built a lot of programs on Mac OS. We have some Linux machines around, but even into GPUs. Like, I guess, do you have recommendations from your experience, Brandon?
So it depends very much on the use case. It's kind of interesting. So the RL policies that are used to train robots to walk, I think it would be this really
RL being reinforcement learning, right? Just to
yes, yeah, okay, yeah. So you've got this reinforcement learning policy that is supposed to get the robot to walk and do all kinds of crazy things. You think you need really advanced hardware, and you do need good hardware to train it. Like you do want a GPU. Honestly, like a 4000 series GPU is plenty to train something like that. It's called PPO, Proximal Policy Optimization. And that training can take a little while, but once you have the policy, it can run on the CPU. So you don't need a GPU-based computer to run some of these complicated things. Now, if you're doing vision language action model, or you're trying to do some LLM, or you're trying to do something that needs more memory and needs to be parallelized, you do need a GPU. And NVIDIA Jetson, those would work great.
Mhm.
And that does require a special type of architecture when you're compiling things. And Viam does that out of the box. So as
Mhm.
you're trying to get this stuff set up, we do have set up to make that easier. And if you're trying to run something that doesn't need a GPU, something like a Nook would work great. I think we use
Mhm.
System 76s, or if you just got an old computer laying around. The answer really is just use what you got, and if you have money, and it's supposed to be rugged, buy a rugged machine. And if you need something like really energy efficient, then you start looking at some of the kind of smaller NVIDIA Jetsons.
Cool. All right,
So
we're running close to time, just to be conscious of that and kind of help start to help people know where to go next after this, right? So obviously, if you haven't finished VM 101 yet, or you haven't even checked it out and started, go try out VM 101. It can take you 90 minutes, it could take you 30, it could take you longer. It doesn't matter. We now have fixed a known issue that people have brought up before, where if they left it and came back, they have to restart from scratch. You have been working actively on that to make sure that people have this sort of session persistence, so we're not losing track of that, and so they can do a little bit of time rather than spending 90 minutes up front or plus. And definitely, if you take longer 90 minutes, doesn't mean you're being slow or anything else. It's like you're taking your time, learn about it, do it at your own pace. That's one of the nice things about this. You don't have to fit it into this allotted amount of time. And then we have those other upcoming courses that you mentioned before. And so you can learn all about those, and even upcoming tutorials we'll be putting on the docs, such as, we have several in the works for the SO101 to get started with it, to start learning about even transferring your knowledge from the palletizer in VM101 to the physical world. So how do you do palletizing with something like the VM, like the SO101, with like dice or 3D printed cubes and some fun stuff that way, and put it into practice, or even starting to do, like we mentioned before, VLA training, exploring other support for other arms or other applications on either a tutorial or a full course. We mentioned before also the Discord. We're going to be there. Brandon and I are there all the time answering questions. That's a place to ask questions, or even to look for people to collaborate with. We have a Jobs and Collab channel. We have our general discussions, and we're always looking to add more people there to see, share what you're building, get feedback. And it's, we've had, it ebbs and flows, but we're there if you have questions, and we're always observing kind of what's going on. And if it takes us some time, we apologize, but we're, going back and forth between Discord and our own internal communication channels as well.
Show us what you're building. We are super excited. I cannot tell you how excited I am to see people's personal projects, even if it's like a tiny little Arduino-based robot that just looks outside and then spits out a treat when their dog comes by, or something ridiculous like the Megabot, which is it was a 3-story tall robot that could pick up a car with one hand, and they replaced the other one with like a chainsaw. It was extremely fun project. I love to see them all.
Yeah, and I also want to know what you want to know about next. So we're always looking at what courses we should do next. We want to hear from you. So do you want to learn more about perception? We talked a little about computer vision, object detection, things like 3D reconstruction, where you get a bunch of point clouds, you want to know where they're at. Navigation. So do you want to learn about SLAM, obstacle avoidance, mobile bases? Do you want to learn more about the machine learning side of things? So if you capture data, how do you label it? How do you train something and deploy it and evaluate it? Or is it more you're looking at like going from one robot to hundreds or thousands? You want to learn about managing a fleet. How do you reuse that configuration somewhere? How do you provision a robot in the field? Those over-the-air updates or OTA we talked about earlier, or even getting alerts when a robot goes down or has issues, or you're getting like drift along your sensors. Like, how do you set that up? These are all topics we can cover. It's a very wide platform, so we want to know what you want to do next. So add that in the chat, and we'll keep that in mind as we're starting to prioritize the next set of courses and tutorials we're building. Anything last for you, Brandon, at all? Any last words?
I am very excited to be here, and for everyone who is watching, our success comes from your success. So if you have questions, please reach out. We are here for you guys, and it's a ton of fun.
Yeah, I hope to see you at future events. We're going to do a bunch in New York. We're going to start going at other places. I think we're going to be at IROS in September if you're in the Pittsburgh area. And we're looking at other events to go. So, send us an email where you should be going, attending events in your area, especially in the Northeast where we're mostly located. I know, I don't know if you want to say where you're at, Brandon, say if there's local meetups or anything that we should be checking out, please let us know in Discord, in our emails, wherever you have. On socials, we're at Viam Robotics in most places, whether it's like Twitter or Blue Sky or Instagram, wherever. Please reach out. Cool. Well, I think that wraps it up for us today. Thanks for joining us, and we hope to see you next time. We're hopefully, as we get to more of a cadence of this, we have more courses we're announcing. Hopefully we do this more, and it's been great chatting with you today, Brandon.
You too, Nick. It was awesome.
Yeah. All right. Great to see you all, and that's it for us here at Viam.